Welcome back to another episode of Second Career Pilot.
Yeah, great to be back.
For anyone out there who's just starting their aviation journey, thinking about becoming a pilot, well, there's one thing that's absolutely key to understand more than anything else.
Besides, how to actually fly the thing.
Right. Besides the actual flying part. And that's the aircraft itself.
Mm.
I mean, what is it? What are all the different types out there? And why are things like airworthiness and design standards so important?
It's like before you even get to lift off, you got to know what you're sitting in. Like, think of this as getting familiar with, I don't know, the nuts and bolts of the machine that's going to take you up in the air.
Exactly.
We're going to be using some pretty solid resources for this, like the FAA's Pilot's Handbook of Aeronautical Knowledge.
Oh, yeah, the handbook. That's the Bible.
It's a good starting point. We'll try to cover the fundamentals, the kind of stuff that'll make you go, oh, okay, I get it now, when you start looking at how these things are built and why they're built that way.
Okay, so first things first, right? What exactly is an aircraft? I mean, the FAA defines it pretty simply: any device that's used or meant to be used for flight.
Sounds straightforward, right?
But then when you think about it, there's a ton of variety out there. Airplanes with their fixed wings, engines pushing or pulling them forward, creating lift. Then you've got helicopters and other rotorcraft.
Yeah, using those spinning blades to generate lift.
It's amazing.
And it doesn't stop there. There are gliders riding the air currents, lighter than aircraft, like balloons.
Oh, right.
Then there are those cool powered lift aircraft taking off like a helicopter, then flying like a plane, powered parachutes. You even have weight shift control aircraft where you literally move your body to steer. It's incredible the different ways humans have figured out how to fly.
It's really wild, yeah.
It is.
And the handbook even talks about advanced avionics aircraft, not a formal category like those others, but refers to aircraft with, well, advanced avionics. Things like GPS navigation systems, moving map displays, often integrated with autopilot.
Yeah, those are pretty standard these days.
Right. So for someone learning to fly today, a lot of the aircraft they'll encounter will probably have these features. It really changes how you approach navigation.
Definitely does. Shows how aircraft design and the tools we use as pilots are always moving forward.
Absolutely. But
Yeah.
the thing is, no matter how fancy the technology gets or what kind of aircraft it is, the design and manufacturing still have to go through really rigorous checks. That's where the FAA's role in certifying aircraft, making sure they're airworthy, comes in. It's a big deal.
Huge. They don't just look at the whole aircraft either. It's the engines, the propellers, the whole package, and it all comes down to these airworthiness standards. You'll find them spelled out in the Code of Federal Regulations, Title 14, often called the CFR.
The CFR, okay.
The whole point is to make sure aircraft are designed right, without any unsafe features. Now, what's interesting is you've got different categories of aircraft, and each one has its own specific set of standards.
Oh, I see. Tailored to what they're designed to do.
Exactly. It's a bit like building codes. You wouldn't build a skyscraper with the same rules as a house, right?
Makes sense.
So,
So let's say you're looking at, I don't know, a normal utility, acrobatic, or commuter category airplane. Those are the ones you might be training in.
right.
Those fall under 14 CFR Part 23.
That's the one.
But a big commercial airliner transporting hundreds of passengers, that's Part 25. Way stricter because, well, it needs to be.
Definitely. And it's the same across the board. Smaller helicopters, the normal category rotorcraft, they're under Part 27. Larger transport category helicopters, Part 29. Even manned-free balloons, they've got Part 31.
Wow.
Engines are under Part 33, propellers under Part 35. So you can see it's pretty comprehensive.
Like a big safety net.
Exactly.
Now, the handbook mentions special classes of aircraft.
Yes.
Gliders, powered lift, things like that. They don't have their own dedicated set of airworthiness standards. How does that work?
So with those, the FAA and the aircraft designers, they basically figure out the best mix of requirements from the existing standards, parts 23, 25, 27, 29, to ensure that particular aircraft is safe for what it's designed to do.
So it's a more, customized approach.
You could say that, yeah.
Okay, so once the design is all good, meets all the standards, then the FAA issues a type certificate, or TC. Sounds important.
It is. It's like the FAA saying, yep, this design checks out. It meets all our safety requirements. And along with the TC, they issue a type certificate data sheet, or TCDS. This document is full of key details, all the important design and operational characteristics of the aircraft.
Like it's blueprint and specs, all in one.
Yeah, pretty much. And if you want to geek out on a specific aircraft type, the handbook says those TCDS documents are available to anyone on the FAA website.
Oh, that's handy.
Definitely is.
Now, light sport aircraft, or LSA, they're a bit different, right? I remember reading that they're not designed to those same FAA airworthiness standards.
That's right. They use industry consensus standards. So, standards that experts and organizations within the industry have agreed on. The FAA recognizes those as acceptable for this category of, smaller, more recreational aircraft.
Okay, so it's kind of a different pathway to getting approved.
You could say that.
Yeah.
And the certification process itself is different too. The type certificate for an LSA actually covers the whole aircraft. So the airframe, engine, propeller, all is one package.
So no separate TCs for each part.
Nope, it's all streamlined under a single TC. Makes sense for LSAs, given how they're designed and used.
Makes sense. Okay, so we've got the design approved, the TC issued. What's next? Now we need to actually build the aircraft.
Exactly. And whether it's a big manufacturer or someone building in their garage, every single part has to be inspected. They have to make sure it's built exactly as the approved design says. This is called a conformity inspection. Super important to ensure everything's built right and consistently.
Right, so no cutting corners. Then, once the whole thing is assembled, airframe, engine, propeller, all of it, there's a final inspection.
Right.
If everything checks out against the design and manufacturing standards, that's when the FAA issues the airworthiness certificate.
Yep, the document that says this aircraft is good to go, safe to fly.
And you have to have that on board whenever you're flying.
Always. It's basically the aircraft's permission slip to be in the air.
Like a driver's license for an airplane.
Kind of, yeah. And just like with a license, it's not a one-time thing. You have to keep up with the required maintenance and inspections.
To keep it valid.
Exactly. Now, there are two main types of airworthiness certificates, standard and special.
Okay, what's the difference?
The standard one is printed on white paper, and that's for those normal, utility, acrobatic, commuter, and transport category aircraft, manned free balloons, and the special class aircraft, too.
Okay, so the ones intended for, I guess you could say, regular use?
Pretty much.
What about the special certificates?
Those are on pink paper, and they're issued for aircraft that operate under specific conditions or limitations. So things like primary restricted limited category aircraft. Light sport aircraft, provisional certificates, those are used during the initial certification process. Special flight permits, sometimes called ferry permits, which are used to move an aircraft that might not currently meet all the airworthiness requirements, and also for experimental aircraft.
So that pink paper is a good visual cue that there are specific things to be aware of with that aircraft.
Exactly.
Okay, so now we've got a certified airworthy aircraft. Let's talk about what actually makes it fly. The handbook lays out these 4 forces of flight: thrust, drag, weight, and lift. They're like the fundamental principles, right?
They are. They basically dictate everything about how an aircraft performs in the air.
So thrust,
Yeah.
that's the forward force, usually created by the engine and propeller, or a jet engine if it's a jet.
Right, that's what gets you moving. Then you've got drag, which is the resistance from the air as the aircraft moves through it. It's always trying to slow you down. Then there's weight, the force of gravity pulling everything down.
And lift is what counters that.
Exactly. Lift is the upward force created by the wings as air flows over them. It's what keeps you up in the air.
And to fly straight and level, all 4 of those forces have to be in balance.
Right. It's a constant interplay of these forces.
And these forces are also acting in relation to how the aircraft moves around its 3 axes.
The longitudinal, lateral, and vertical axis, yeah. Imagine a line running through the aircraft from nose to tail. That's the longitudinal axis. And the movement around that axis, controlled by the ailerons on the wings, is called roll, like tilting your head side to side.
Oh, okay, got it.
Then you have the lateral axis, running wingtip to wingtip. Movement around that one is called pitch, and it's controlled by the elevator on the tail. It's like nodding your head up and down. And lastly, you have the vertical axis, going straight down through the aircraft's center of gravity. Movement around this one is yaw, and it's controlled by the rudder on the tail, like shaking your head no.
That's a good way to visualize it. Nodding, shaking, tilting.
Yeah, exactly.
Now, something the handbook really emphasizes is the center of gravity, or CG, the point where the aircraft would perfectly balance. Why is it so important to know where that is?
Because it affects the aircraft's stability, big time.
Yeah.
You know, if the CG is too far back towards the tail, the aircraft can become really unstable, almost impossible to control.
So it needs to be in the right place.
Absolutely. And the handbook gives an example about fuel tanks being located in front of the CG. As you use up fuel during flight, the weight shifts rearward.
Oh, I see.
So you have to account for that when you're loading the aircraft and planning your flight.
It's a constant calculation.
It is.
And the handbook mentions that having the CG too far forward or too far aft can affect your ability to control the aircraft,
Yeah.
especially during takeoff and landing.
Oh, yeah, for sure. A forward CG can make it hard to lift the nose for takeoff or to slow down and raise the nose for landing.
And a rearward CG.
That can make the aircraft super sensitive and prone to stalling, and you might not have enough control authority to recover. It's crucial to get it right.
So we've talked about forces and axes. Let's get into the physical parts of the aircraft. The handbook breaks down those major components that most airplanes share, right?
It does. Despite all the different types and purposes, most airplanes have the same basic building blocks.
Okay, so what are those?
Well, you've got the fuselage, the wings, the empennage, which is the tail assembly, the landing gear, and the power plant.
Okay, let's start with the fuselage.
All right. The fuselage is basically the main body of the plane. It houses the crew, the passengers, any cargo, and it connects all the other parts together.
Right. And the handbook mentions that fuselage designs have evolved over time, like from those older truss structures to the more modern monocoque and semi-monocoque designs.
Yeah, that's an interesting bit of history.
It is.
Early aircraft, they used to have these truss structures, basically a framework of beams or tubes made of wood or metal, strong but not very aerodynamic.
Right.
Then you have monocoque construction, which basically means single shell. The idea is that the outer skin of the fuselage carries most of the structural loads, making it stronger and lighter.
Like an eggshell.
Yeah, exactly like that. But the most common design you see these days is semi-monocoque.
Okay, so what's that?
It's kind of a mix of the two. You have a stressed skin, but it's reinforced by this internal substructure of frames, formers, and stringers. Think of it like a soda can. It's strong because of the combination of the thin metal skin and the reinforcing rings.
Okay, I see. So it's like a more efficient way to build a strong and lightweight structure.
Exactly. And it's relatively easy to manufacture and repair.
Makes sense. All right, next up, the wings. The things that actually generate lift. They come in all shapes and sizes.
They do.
And the handbook talks about how they're attached to the fuselage. High wing, mid wing, low wing. Then there are monoplanes with one set of wings and biplanes with two.
Yep. All those configurations have their own advantages and disadvantages, both aerodynamically and structurally.
Makes sense. And the wings themselves are more than just a smooth shape.
Oh.
There are spars, ribs, stringers. What are all those?
Those are the structural components that give the wing its strength and shape. The spars are like the main beams that run along the length of the wing, carrying the load. The ribs give the wing its aerodynamic cross-section, the airfoil shape, and support the skin.
Okay.
And the stringers are these lighter lengthwise members that add stiffness to the skin and help distribute the load more evenly. It's like a carefully engineered skeleton inside the wing. And interestingly enough, in a lot of modern aircraft, the fuel tanks are actually integrated within the wing structure itself. Makes use of the space, keeps things balanced.
Smart. All right. And on the trailing edges of the wings, we've got the control surfaces, the ailerons and the flaps.
Right. Those are what allow the pilot to control the roll of the aircraft and to increase lift when needed.
So the ailerons, they're near the wingtips and move in opposite directions.
Right. When you turn the control wheel, one aileron goes up, the other goes down, creating a difference in lift between the wings. That's what causes the airplane to roll.
Okay. And flaps.
Flaps are usually closer to the fuselage on the trailing edge, and they move down together. This increases the curvature of the wing, generating more lift. Super important for takeoff and landing because it allows the aircraft to fly slower and safer at those critical moments. The handbook even shows different types of flaps. Plain, split, slotted, Fowley flaps, all with slightly different ways of doing that.
That's a lot of variations. All right, moving on to the tail section, the empennage.
Ah, the tail. You've got the vertical and horizontal stabilizers, and those are
Yep.
fixed. Then you have the movable control surfaces, the rudder attached to the vertical stabilizer, and the elevator attached to the horizontal stabilizer.
And the stabilizers themselves, what do they do?
Well, the vertical stabilizer, that's what keeps the nose pointed where you want it. Directional stability. The rudder is what you use to control yaw, that side-to-side movement of the nose.
Okay, so rudder for yaw.
Yep. And the horizontal stabilizer, that provides stability in the pitch axis, prevents unwanted up and down movements. The elevator, that's what controls the pitch, raising and lowering the nose.
So elevator for pitch. Got it.
Yeah.
And what about trim tabs?
Ah, trim tabs. Those are like little helpers. They're small, adjustable surfaces on the trailing edges of the main control surfaces. They allow the pilot to fine-tune things. So instead of having to constantly hold pressure on the controls, you can adjust a trim tab to basically hold the control surface in a specific position.
So it reduces pilot workload, especially on longer flights.
Exactly. You can have trim tabs on the ailerons, rudder, and elevator.
Okay. Now, there's something called a stabilator, which the handbook says is an alternative to the elevator.
Right. So instead of having a separate fixed horizontal stabilizer and a moving elevator, a stabilator is one whole piece that pivots.
The whole thing moves.
The whole thing. But it's still controlled by the control wheel, just like an elevator. However, because it can be more sensitive to control inputs, it usually has this thing called an anti-servo tab on the trailing edge. That tab moves in the same direction as the stabilator, and it helps make the controls feel more natural, less twitchy. It also acts as a trim device.
Interesting. Okay, then there's the landing gear, the part that keeps the aircraft upright when it's on the ground. Usually wheels, but the handbook mentions floats for water and skis for snow too.
Yep, depending on where you're operating. But with wheeled landing gear, the most common type, you usually have two main wheels and then a third wheel. That third wheel can be at the front, which is called tricycle gear, or at the back, which is conventional or tail wheel gear.
I've heard of those.
Yep. And that front or rear wheel, it's usually steerable, allowing the pilot to control the aircraft on the ground during taxiing. Most of the time that's done with the rudder pedals. Some aircraft also use differential braking, applying the brakes on one side more than the other to help with steering.
Makes sense. All right, lastly, we've got the power plant. For smaller airplanes, that usually means the engine and the propeller working together. The engine, of course, provides the power to turn the propeller, which creates the thrust. But the engine often does other things too, right?
Absolutely. Electrical power, vacuum for some instruments, sometimes even heat for the cabin in single-engine aircraft. The engine is like the heart of the airplane, keeping everything running. It's usually covered by a cowling or nacelle, a streamlined cover that helps with airflow and cooling.
Right.
And the propeller itself, that's essentially a rotating airfoil, like a wing but spinning. It generates thrust by pushing air backwards. Depending on where it's mounted, it can either pull the aircraft forward, which is called tractor configuration, or push it from behind, pusher configuration. Yeah, and the angle and the pitch of the propeller blades. Those are key factors that affect how efficient it is at different airspeeds.
Now, for someone stepping into the cockpit for the first time, there's a whole bunch of instruments to understand. The handbook talks about the evolution of aircraft instrumentation, from those individual analog gauges to those fancy electronic flight display systems, or EFDs, that use LCD screens.
Yeah, technology has come a long way.
It has. So what are the main differences between those older systems and the newer ones?
Well, these EFDs often have a primary flight display, or PFD, right in front of the pilot.
Okay.
That shows all the key flight information, like airspeed, altitude, attitude, heading, all in one place. Many aircraft also have a multifunction display, or MFD, which can show things like navigation data, engine information, all sorts of other important stuff. These digital displays have really helped to declutter the cockpit. And they're generally more reliable, too, since they're solid-state electronics.
Makes sense. But it's still important to understand how it all works, even with all the automation, right?
Oh, absolutely. The handbook makes a big point of that. No matter what you're flying, whether it's got old school gauges or a glass cockpit, you need to know what those systems are telling you.
Right. No matter how much help the systems give you, you still got to know how to fly the plane.
Exactly. Now, the basic categories of flight instruments, those haven't changed. You have performance instruments, control instruments, and navigation instruments. Understanding what each one tells you is essential.
Let's break those down. So performance instruments, those tell you how the aircraft is actually doing in the air, right?
Yep. Things like your airspeed, altitude, rate of climb or descent, heading, even things like angle of attack and whether you're slipping or skidding.
Important stuff.
Crucial stuff. The airspeed indicator shows how fast you're moving through the air. The altimeter shows your height above sea level. The vertical speed indicator shows how quickly you're gaining or losing altitude. All essential information.
Got it. And what about control instruments?
So control instruments show immediate changes in attitude and power. The attitude indicator, which shows the aircraft's pitch and bank relative to the horizon. That's the big one here.
Okay, attitude indicator.
Right. It basically gives you a visual reference of the aircraft's orientation in space. And while those control instruments show the immediate changes you're making with the controls, you need to cross-reference that with your performance instruments to see how those changes are actually affecting your speed, altitude, and so on. It's a constant back and forth.
All connected. And finally, navigation instruments.
Ah, yes. Those tell you where you are and where you're going.
Right. Relative to different navigational aids or points on the ground, the handbook mentions things like course indicators, range indicators, glide slope indicators, bearing pointers. And these days, there are systems that can combine information from different sources for even more accuracy.
Right. Modern navigation instruments can show data from systems like GPS, VOR stations, NDB transmitters, ILS signals, all sorts of things that give you guidance. Two-dimensional, just for lateral navigation, or three-dimensional for approaches where you need vertical guidance as well.
And speaking of GPS, it's become so commonplace in aviation.
Yeah.
That's the global positioning system, right?
Yep, it's a satellite-based system, originally developed by the military, but now widely used by everyone.
It's amazing how it can pinpoint your location almost anywhere.
It really is. And it works in pretty much all weather, 2004-7. Your GPS receiver needs to be picking up signals from at least 4 satellites to figure out your exact position, including altitude, super accurate and reliable.
Wow. So we've covered a lot of ground today, from what defines an aircraft to the parts that make it fly, and even a look at the instruments you use to control it all.
A lot of information, but it's all foundational. As you go further in your aviation journey, keep in mind that understanding these basics is key to flying safely and confidently. The more you know about your aircraft, the better prepared you'll be as a pilot.
Absolutely. And, keep exploring.
Yes.
Dig deeper into these topics. The handbook's a great starting point, but there are so many resources out there. Look up those CFR parts we talked about.
Yeah, check out the type certificate data sheets for different aircraft. They're all on the FAA website.
It's amazing how much information is available. And as you start your flight training, really try to connect what you're learning about aircraft design and airworthiness to what you're experiencing in the cockpit.
Exactly.
Think about how the CG affects the handling.
Yeah, and what happens when you move the controls? How do the ailerons, elevator, and rudder respond to your inputs?
What makes you curious about these incredible machines?
What questions do you have about the engineering and the regulations that make it all possible?
Keep asking those questions. That's what keeps us learning and growing as pilots.
Couldn't agree more.
Thanks for listening.